So we looked at this paper that argued that 2023-24 El Nino was not coupled to the atmosphere. It was an ocean dynamic El Nino. Bjerknes feedback didn't happen or was very weak compared to the earlier El Ninos. There was an earlier paper led by Amy Clement of Miami, which had argued that there is a thermally coupled Walker mode, which looks like an El Nino in the sense of the Southern Oscillation. Remember, Southern Oscillation was coined by Gilbert Walker in the 1920s as the Darwin-Tahiti pressure oscillation, sea level pressure. He was interested in the impact on monsoon, the droughts, the famines, and El Nino as a terminology evolved much earlier in the 18th century or so by the Spaniards colonizing South America. Bjerknes in the 1969 paper argued that there was a strong coupling between the ocean, the upwelling, thermocline movement, wind response, SST gradient, sea level gradient, and you had growing warming mode and growing cooling modes, and then you need to terminate the growth with waves and recharge, discharge, etc. This idea here is to look at ocean's role in the Southern Oscillation. It's a long paper with lots of model experiments and comparing coupled models to forced SST atmosphere models and something called slab atmosphere model, which means you prescribe ocean as just a slab mix layer which has heat transport, so you have some kind of a thermal coupling. If you just prescribe SSTs, then obviously ocean has not been prescribed dynamically. Somehow you got the SSTs and you're just giving it, and the atmosphere just responds to it. So I'm going to be brief basically because I want you to be aware that there is El Nino. We keep on saying it's a coupled mode, but there are El Nino-like modes either in the Southern Oscillation or in the ocean that can be done without coupling. We have to just keep that in mind. And as we saw in the ocean dynamic El Nino of 23-24, the authors argue that maybe these sorts of El Ninos will increase because we have Atlantic and Indian Ocean warming happening, which can perturb the Walker cell, create trade wind anomalies, and of course ocean can accumulate heat because you have multi-year La Ninas, which are always, El Nino is a single year event mostly, and La Nina can be multi-year event, and there are reasons for why that happens. Maybe I will have a podcast on that as well. So coming back to this paper, long prologue, but the Southern Oscillation is usually described as the atmospheric component of the dynamically coupled El Nino Southern Oscillation phenomenon. The contention in this work, however, is that dynamical coupling is not required to produce the Southern Oscillation. Simulations with atmospheric general circulation models that have varying degrees of coupling to the ocean are used to show that the Southern Oscillation emerges as a dominant mode of variability if the atmosphere and ocean are coupled only through heat and moisture fluxes. So somehow ocean heat varies and moisture flux, latent heat flux varies because of that. Then you can generate this pressure mode. Here in this mode of variability is called the thermally coupled Walker mode because you're still perturbing the Walker cell through the Southern Oscillation. It's a robust feature of simulations with atmospheric general circulation models coupled to simple ocean mix layers. So ocean dynamics in terms of the thermocline and the SST change and the wind response, etc., are not involved as in the Bjerknes feedback. Despite the absence of atmospheric general circulation models coupled to despite the absence of interactive ocean dynamics in these simulations, the spatial patterns of sea level pressure, surface temperature, and precipitation variability associated with the TCW are remarkably realistic. This mode has a red spectrum indicating persistence on interannual to decadal time scales. So some color exists in terms of time scales that appears to arise through an off-equatorial trade wind evaporation surface temperature feedback, what we often called WES feedback, and cloud shortwave radiative effects in the central Pacific. When dynamically coupled to the ocean in fully coupled ocean atmosphere GCMs, the main change to this mode is increased interannual variability in the eastern equatorial Pacific sea surface temperature and teleconnections in the northern Pacific and equatorial Atlantic though not all coupled GCMs simulate this effect. So they find it in some models, and they say that when ocean dynamic coupling is involved, Eastern Pacific lights up and then there is an Atlantic response. Remember, with a coupled mode, we are thinking the warm pool is moving, convection is shifting, cloud feedbacks happen, Bjerknes feedbacks happen. But if you can generate a Southern Oscillation response, then you have to answer how trade winds weaken, what happens to the clouds, etc. So they do that in this, but I may not go through all the details. Despite the oversimplification due to the lack of interactive ocean dynamics, the physical mechanisms leading to the TCW should be active in the actual climate system. Moreover, the robustness and realism of the spatial patterns of this mode suggest that the physics of TCW can explain some of the primary features of observed interannual and decadal variability in the Pacific and the associated global teleconnections, which means you have to understand which of the El Niños are simply TCWs, where Southern Oscillation is producing the teleconnections, precipitation responses, and which ones are strongly coupled. Obviously, we are sitting here in 2026. I'm recording this on August 2nd, and the 26-27 El Nino is booming, generating all kinds of headlines and infinite postings on social media by pretty much everybody. So here is a figure, monthly SO index, Southern Oscillation index, which is in sea level pressure difference within the deep tropics, 5 south, 5 north, over 100 degree west and 180 degrees. So dateline to 180 degree west, minus 5 south, 5 north, and 90 degree to 140 degree east. So obviously we are trying to simulate Darwin and Tahiti, but looking at the tropical Pacific. Walker did Darwin and Tahiti because he had data from there. In the ocean, Tahiti is an island, and he could get data in the Eastern Pacific from an island, but now we don't have to rely on island data, so we can do these things. So the black curve here shows the low-pass filtered Southern Oscillation Index 10-year cutoff period, basically arguing that there is the intra-annual, so seasonal scale variability, interannual variability, which is obviously you can see 82, 83, 86, 87, 97, 98, 93, 94, that period, and so on. All the big El Niños can be seen. So in the second figure, they basically regress things. So this is the Hadley sea level pressure regression on 10-year high frequency high pass Southern Oscillation Index, which produces this kind of a feature. So here SLP 10-year HPSO index, and you can see the actions again more in the southern hemisphere, but there is also a northern hemisphere signature. This is the same thing, but low pass filtering of the index. So you can see now you get a similar structure, but much weaker. So you can see the sea level pressure delta HPA here, delta SLP. So the colors are brighter, 0.5 or so to minus 0.5. Here they are weaker, so 0.1 to 0.2 and minus 0.2 to 0.3 or so. So if you do the same thing with multi-data set SST regression, when you do high-pass SO index, you get the El Nino-like feature in SST. And you can see climatological SSTs laid on top, and climatological sea level pressures, high pressure, low pressure, relatively speaking. And this is the low frequency, and this is called ENSO-like variability. This is what they are going after. So there is a ENSO variability, which is predominantly interannual. There is ENSO-like variability that is decadal, multi-decadal. So you have to try to explain all these things, which is what they are doing with lots of model experiments. And you can see when they force the community atmospheric model with climatological SSTs, you get basically the leading EOFs of monthly normalized sea level pressure anomalies. And this is the CAM slab. So you give it thermal thermodynamic coupling, so you produce the east-west contrast here, and C here is in the CCSM, which is the coupled model. So the variances explained by the mode are shown here: 72%, 28%, and 50% respectively. And there are differences in the power spectrum density as well when you look at each of these modes. Okay, so I'm being brief because basically I want to focus on the fact that we are trying to do these series of El Nino podcasts, and I want to keep it simple but want to raise all these issues that you can follow up with. El Nino, we always think of it as ENSO El Nino Southern Oscillation, because at some point it was decided that Bjerknes feedback is a big part of the El Nino. So we have ENSO warm and ENSO cold events, so El Nino and La Nina, even though El Nino and La Nina also persist as terminologies. But there are now arguments that maybe ocean dynamics can do something in a global warming world, and there's always been a thermally coupled southern oscillation that can produce global teleconnections similar to El Nino as well. That's the main message, okay? And this group does lots of experiments to find all sorts of mechanisms to explain wind changes, cloudiness changes, and the variability seen in SO without full coupling, and they compare to full coupled model as we see here. Okay, so how does the thermally coupled Walker mode work? The ENSO-like SST warming pattern comes about primarily from weaker northeast and southeast trade winds, so the trade winds are still involved. To illustrate this, we show the regression of various fields onto the 2-year low-pass filtered tendency of the Southern Oscillation DSO-DT, which I'm not showing here. The regressions indicate what this mode looks like as it is developing. We use a 2-year low-pass filter to emphasize the effects of mixed layer integration. Figure 8a, which I skipped, shows that the integrated heating associated with the developing SO indeed looks like the pattern of SST anomalies associated with the Southern Oscillation, which they show in figure 7a, and the magnitude of the net heat flux, maximum of about 4 watts per meter squared, is consistent with a warming of 0.2 Kelvin for a 50-meter mixed layer on a seasonal time scale. So we're talking about thermal inertia. Remember, when you have full Bjerknes feedback, the mixed layer is varying fully, and the amplitude of the SST variance and mixed layer variance and mixed layer thermocline interactions, etc., are much stronger in the east, as they said in the earlier part of this paper. This warming pattern mainly comes from the latent heat flux, so this thermal coupling, wind evaporation SST feedback, which is shown as positive into the ocean. So ocean loses heat or gains heat depending on which phase you are in. The reduced, or it's always losing heat, but less or more depending on the SST anomalies. The reduced latent heat flux coincides with a weakening of the trade winds, which is consistent with a wind-induced latent heat flux change, since there is little SST signal in those regions. The off-equatorial cooling in the west is also consistent with the altered circulation. Southerly advection warms the western basins, as was shown by Richard Seeger in another paper. So weaker advection is consistent with cooling. There is also an increase in the westerlies, which would lead to cooling by induced latent heat flux. So we're talking about wind evaporation SST feedbacks. We note that a change in wind speed is not well captured using monthly mean wind components, since the subtropics and mid-latitudes mean wind speed is dominated by transient eddies, so high frequency synoptic scale variability. However, sub-monthly data for calculating the wind speed are not available for many of these simulations which they are using from the databases that are available. As this mode is developing, there is little temperature change in much of the tropical Pacific. There is a small warming in the eastern subtropics where the trade winds are reduced, consistent with the reduced latent heat fluxes, particularly in the southern hemisphere. Why did I skip all those? Basically, I'm being a little bit lazy, but you understand the point that they have to answer how the trade winds get weaker, and what happens to the clouds, and they argue that there is a shift in convection and clouds, and trade winds weaken because of this thermal coupling and wind SST evaporation feedback, and then they invoke the meridional mode, etc., which is mentioned here, as we'll see. This multi-model analysis has shown that Pacific climate analysis, this multi-model analysis has shown that Pacific climate anomalies that have an ENSO-like spatial structure with warming in the eastern Pacific, eastward shift in the convection and Walker circulation perturbations, so weaker Walker circulation when SST is warm in the east, can develop on interannual to decadal timescales without dynamical coupling to the ocean, i.e. with no Bjerknes feedback. Here we discuss the implications of this result for Pacific climate variability on different timescales. So they look at interannual and decadal timescales, which are the critical timescales, and there are lots of details on decadal timescale variability and El Nino and La Nina and how they are related to each other. But there is always this idea of a decadal ENSO-like variability, which is also what often is referred to as a Pacific decadal oscillation. And there has always been an issue that PDO, Pacific Decadal Oscillation, doesn't seem to have a real mechanism. It is a robust mode, and people argue that it's a superposition of El Nino and La Nina because El Nino is more symmetric around the equator and La Nina is not, and when you superpose them, you get this kind of a PDO-looking mode. Why am I going there? Because that's very important in the way these people are trying to explain the uncoupled, thermally coupled Walker mode. Interannual timescales, then, it has previously been suggested that observed El Nino events are preceded by a weakening of the northeast trade winds in Boreal Spring. Chang et al. Argue that a meridional mode that links variability in the North Pacific to the deep tropics influences the equatorial wind stress, which can then trigger the event. We looked at this already, and we also said there is also a Southern Pacific mode, Southern Pacific meridional mode, which is slightly different, but acts more on the Eastern Pacific as opposed to the Northern Pacific meridional mode, which comes in the Western Pacific and so on. Right, so the meridional mode develops through a wind evaporation surface temperature feedback that does not require dynamical coupling to the ocean. A more recent observational study by Thierry Pascal shows that a similar meridional mode also operates in the southern hemisphere and can be used to predict El Nino events with some skill because it leads by a few months. Our results are consistent with this interpretation of the observations from both the northern and southern hemispheres. That is, variability in the trade winds of both hemispheres with a pattern like that shown in 8D, which you please look up, influences the net surface heating, yielding an SST pattern that has an ENSO-like structure that develops on interannual timescales. No Bjerknes feedback needed. This interpretation is also consistent with an earlier observational analysis of Penland and Deshmukh, who showed that optimal surface temperature pattern that gives rise to El Nino events 7 months later in their figure 6 looks very much like the pattern shown in the figure 8E here, i.e. the developing pattern of SST. Penland and Deshmukh were just trying to see if statistically they can do El Nino predictions, so they always find these, what do they call it, the canonical pattern. I just said it here. Penland, who showed that optimal surface temperature. Okay, sorry, I got lost there a little bit. We interpret this temperature signal in the multi-model analysis as being the surface expression of the trade wind variability shown in figure 7D, i.e. the same temperature change that occurs within a short or less than 2-year time in response to a wind-driven change in latent heat flux. So you have global scale trade winds. Pacific dominates with its large scale, and trade winds can weaken and strengthen on their own, and they don't necessarily have to always involve Bjerknes feedback, but they do involve pressure oscillations similar to the Southern Oscillation. So I have to explain where all these things come from. Not that we have explained El Nino completely in terms of exactly how it starts. Once it starts, we can always put phase diagram and see how it grows, especially when it's strong. And we say recharge discharge oscillator can explain the fact that it's a stable oscillator, but then the periods vary, then you invoke stochastic variability and so on and so forth. So this interpretation of the Pendland-Sadeshmukh pattern also provides a mechanism by which the off-equatorial SST pattern can be related to changes along the equator, since there's an equatorial mass flux divergence associated with the trade winds, which is atmospheric process. So your trade winds are moving masses, which is sea level pressure variations. There's no doubt that coupled ocean dynamics can amplify an ENSO-like perturbation on intraannual timescales via the Bjerknes feedback. However, these results suggest that the development of ENSO-like variability on intraannual timescales is expected without Bjerknes feedback via thermodynamic coupling between the ocean and the atmosphere, as previously suggested by Hamid in 1989, Zhu and Carton, and so on. And the TCW mechanism may contribute to the development of ENSO events. Furthermore, this mode of variability is a robust feature of all AGCM slab models. So if we haven't explained exactly how El Nino starts, maybe this intrinsic thermally coupled Walker mode can say that sometimes this Walker mode gets more than thermally coupled and becomes Bjerknes feedback. Okay. At decadal time scale, then the slab model results show that variability in the SO can be expected on decadal time scales as a result of weak damping. If you don't know what is slab model coupling, then you have to go and read it. But basically, you can give a full ocean GCM, in which case thermocline moves, entrainment happens, coupled SST gradients, pressure gradients, wind responses, all these things happen. But when you give it a slab, you are just moving heat around in the mix layer to provide thermal response of the ocean without the dynamic response, because ocean does move heat around. And if you don't move the heat around, you will end up with a unrealistic SST pattern, because the ocean is part of moving the heat towards the poles for, getting rid of this excess energy in the deep, in the lower latitudes, and atmosphere does the work in the higher latitudes of moving energy towards the poles, right? Some models, such as the MRI, simulate variability out to multi-decadal timescales, perhaps because of a positive cloud feedback. So if you only have a thermodynamic ocean, then where does the memory come from for decadal, multi-decadal variability? This you have to explain as well. So they are invoking cloud feedback, but decadal timescale can come as a result of weak damping. So you go and read the paper to understand what that means. Inclusion of a large-scale ocean heat capacity with beyond a 50-meter mix layer could introduce variability on even longer time scales, because if you give that gives you ocean memory, then you can generate lower and lower frequencies, right? So this is done by Dominguez and Latif. On the other hand, they call it hyper mode and so on. Basically, sun is in the one hemisphere for 6 months, in the other hemisphere 6 months, and ocean is deep, so it can accumulate heat and release it at various time scales. So you can generate lots of time scales when you have memory of the ocean involved. On the other hand, interactive ocean dynamics in some coupled models can also produce enhanced power in the Southern Oscillation on decadal timescales relative to their slab components through a rectified effect of intraannual timescale variability. So low frequency rectification of high frequency variability is very common. You can think of it as part of the recharge discharge also. Okay, these results suggest that the power in the SO at decadal timescales can be thought of as being the combination of multiple processes, mixed layer integration of stochastic forcing with weak damping, and a possible rectification of strong nonlinear intraannual variability. So ocean can integrate weather timescale forcing to produce low frequency variability. That's what we mean here by stochastic forcing with weak damping. However, the balance of these processes is quite model dependent, and hence it's important to provide some observational constraints on these processes, in particular to the extent that damping rates in the Eastern Pacific Basin may depend on low cloud feedback, and that low-level clouds are poorly simulated by the models, etc. And they suggest also that one can go and look for these evidences in the paleoproxies. To conclude, basically, we have revisited the explanation of the Southern Oscillation without presuming a role for interactive ocean dynamics in its spatial and temporal characteristics. Our main finding is that models can simulate variability in the tropical Pacific climate that has the spatial structure of the Southern Oscillation without dynamic coupling to the ocean. Simulations with the community atmosphere model CAM show that in the absence of thermodynamic coupling to the ocean, the dominant mode of sea level pressure variability in the Pacific is a zonally symmetric structure, and the spectrum of this mode is white. Zonally symmetric basically means ddx is not very strong, it's zonally uniform. Thermodynamic coupling to an ocean mix layer produces a dominant SO mode of variability with spectrum that is red, consistent with a stochastically forced weakly damped process. So we saw so this is what you would basically call zonally symmetric. You here ddx is almost zero, and here ddx is strong in both these cases, slab and mixed and coupled. Okay, taram param, where were we? Okay, these results suggest that oops, already I was here. This mode of variability, which we refer to as the thermally coupled Walker mode, appears to be tied to the weakening and strengthening of the trade winds, which leads to an ENSO-like SST pattern, an east-west shift in the convection in the Central Pacific, and a weakening of the Walker circulation and global teleconnections. Everything that ENSO does is done here. The effects of dynamical coupling with the ocean include increasing the amplitude of this mode on intraannual timescales and altering the teleconnections to particular regions, including the North Pacific and Equatorial Atlantic. Otherwise, the pattern in SLP, SST, and precipitation that arise in association with TCW are in very good agreement with observations, and we conclude that the TCW is a mechanism for generating variability on intraannual to decadal timescales in the global climate. So if you take observations and do assume that Bjerknes feedback is always happening, then you will be misinterpreting the system. On a final note, the Bjerknes feedback has received much attention for its role in intraannual climate variability associated with ENSO and has been invoked to explain variability on longer timescales as well. For example, Dijkstra and Nealon invoke a climatological Bjerknes feedback to explain the warm pool cold tank configuration of the Pacific climate, and Clement et al. Argue that Bjerknes feedback is important in the adjustment of tropical Pacific to external forcing. So every season there is a flattening of the SST gradient and strengthening of the SST gradient. Seasonal upwelling is strong in July, August, September, weakest in March, April, May, and there is a climatological Bjerknes feedback because this zonal contrast is always maintained. Right, this is what they are talking about. Our present results suggest that ENSO-like variability can be produced without this feedback, and that Bjerknes feedback only operates as a positive feedback on intraannual timescales, amplifies the thermally coupled Walker mode. Hence, the application of this conceptual feedback is not appropriate for interpreting decadal variability of anthropogenically forced climate change in the Pacific. Slightly different issue, but you can follow up. Dinizio was Amy's student, so they followed up with that work. Moreover, although we have adopted the terminology ENSO-like in this paper to be consistent with the current literature, this study clearly demonstrates that the TCW is not ENSO-like in its mechanism, since there is no role for interactive ocean dynamics. However, the spatial structure of the climate variability of TCW is very much ENSO-like, which again suggests that ENSO-like climate changes need not be explained as resulting from the Bjerknes feedback. So there are many unanswered questions in this sense. Plus, after this paper came, people have not really try to go back and look at how many events were thermally coupled versus Bjerknes feedback, where they're weaker ENSO-like modes or Southern Oscillation. Southern Oscillation does have lots of variability, and there are ideas that the Australian rainfall variability is better explained by the Southern Oscillation than ENSO and so on. So let me leave it here.